Hi, welcome back. This is still Ken, and we're still on our course on mechanics, and we're still on lesson 6, which is about work and kinetic energy. In this lesson, we're going to discuss the work done by a spring. In the previous lesson, we have discussed about the work done by a varying force. A model of a common physical system for which the force varies with the position is the work done by a spring. Consider, for example, you have a block on a horizontal frictionless surface that is connected to a spring, like on the figure to the left. Now, if the spring is either stretched or compressed a small distance from its unstretched, or this is what we call your equilibrium configuration, it exerts a force on the block. Now, looking at the figure, you have there your figure A, or let's look at first your figure B. The figure B configuration is what you call your unstretched or your equilibrium position. That is, your spring is neither stretched or unstretched. So if you're going to stretch the spring at a little distance, let's say you stretch it to the right, there's some little distance x. Okay, you'll observe that the spring, or if you're going to do it by your hands, you're going to stretch it, you are actually going to feel something that pulls it back, and that is you're feeling that the spring is actually pulling the block back, and that is the nature of the spring, to always return it to its equilibrium position. If on the other hand you're going to compress the spring, like in figure C, you'll feel that the spring is actually pushing back on you, because again, the nature of the spring is that it always wanted to go back to its equilibrium position. So there's a force that is there is a force that is applied by the spring as you stretch it, and then also as you compress it. So since there is a force and there is some displacement, the spring actually does a work on your system. So that is why we call it as the work done by a spring. Now, in later examples, we're going to discuss the work done on a spring. So these are two different situations: the work done by a spring and then the work done on a spring. So for the work done on a spring, you will observe here in figure D. Okay, if let's say you're going to compress it at a maximum compression. Okay, so you have here your the work done, the maximum work done. But as you are going to, or how do you call this? As you're going to release the spring, the block, or you're going to lessen the force that you're applying the block, compressing it, you observe that the work done by spring also decreases. Okay, because this time now, the force that is applied by the spring is also decreasing, and it increases. Okay, it increases back again up to the maximum stretch position of the spring. Now you see here that you have your force, which is equal to negative kx. We're going to discuss this one in the next slides. So the force negative kx that we have seen on the previous slide is what you call your Hooke's law. So that is the force exerted by a spring, and it's equal to Fs is equal to negative kx. So why do we have a negative on your equation for your Hooke's law? So it's a negative because it's a restoring force. So as you see, if you're going to stretch this block here to the right, the force that is applied by a spring is negative. It is opposite to the direction of the force that you're applying, because again, it's a restoring force. It restores your system into its equilibrium position. Here, x is the position of the block with respect to the equilibrium position, that is our x equals 0. And k is called the spring constant or force constant and measures the stiffness of the spring. So the greater your k is, the stiffer your spring is, or the harder it is to compress or to stretch. But by the way, your Hooke's law is somewhat really not a, or your Hooke's law is not applicable to all systems. So it's basically not a real law in some sense, because let's say for example, when there is this maximum compression and maximum stretching of your spring, right? There is only this maximum x wherein you can compress your spring, and you cannot anymore compress it to at greater distances. And there's also this maximum stretching of your spring. If you're going to exceed this maximum stretching, okay, your Hooke's law will not be any more valid because you've already reached your, we call this one as your elastic limit for your spring. And by the way, many materials also do not, or somewhat deviate from your Hooke's law. So we can say that your Hooke's law is actually not a universal law in some sense. Now, here, when x is positive, that is the string is, or the spring is stretched, f is negative because again you have your f is equal to negative kx. When x is equal to 0 at the equilibrium position, your f is 0. So you have negative k times 0, it's 0. When x is negative, that is your compressing the spring, f is positive because you have your negative k times negative x, you have positive kx. So your force now is positive. Okay. So the force exerted by spring is always directed opposite to the displacement from the equilibrium. The spring force is sometimes called the restoring force. If the block is released, it will oscillate back and forth between negative x and x. If there are no external forces such as your friction, this movement or this oscillation of your spring will go on forever. That is, it will oscillate back and forth from your negative x and x to, so if you're going to compress it, like say for example to some displacement negative 2, your restoring force from the spring will make it move to x is equal to 2, so you have positive 2, and it will oscillate from negative 2 to 2 until at such time that something or an external force will try to end the oscillation. Now let's discuss the math of the work done by a spring. Suppose that the block has been pushed to the left to a position negative x max, that is the maximum compression of your spring, and then you compress it and then you just release it. Okay, calculate the work done Ws by the spring force on the block as the block moves from your initial position x max to xf equals 0. That is from your maximum compression towards the equilibrium position. Okay, so you're asked to calculate for this work done. Again, if you remember from our previous discussion, your work done is just equal to, for varying forces, you have from your work is equal to the integral evaluated from xi to xf of your fx dx. So we're going to use this equation here to find for the work done by a spring. I'd like you to review about your integration. This is just a basic integration here before proceeding to the actual calculations. Okay, so here we're going to calculate the work done by spring from x max to xf. So we have your xi is equal to the maximum compression negative x max, and then your xf is towards the equilibrium position x equals 0. Now here your fx is equal to your Hooke's law. We have your negative kx. You're going to use this function here for this part of this equation here, and we're going to use xi and xf as negative x max and 0. So looking here at the equation, okay, so you have the integration or the integral of fx dx evaluated from xi to xf is equal to the integral of negative kx dx and then evaluated from negative x max to 0. So here, the integral of this part here, okay, the integral of this part here is just, you have negative k x squared over 2. And we're going to evaluate this one from negative x max to 0. So this is your work done by your spring. So we're going to substitute for 0, and then you subtract it by your negative x max substitution. So this is equal to 0 minus your negative k, and then you have your x max divided by 2. So your final answer is equal to 1/2 k x squared maximum, or you have 1/2 k x max squared. So this is the work done by the spring as your spring moves from the maximum compression, negative x max, to the equilibrium position, xf equals 0. Now next, find the work done, ws, as the block moves from 0 to x max. Now this time, our conditions are the following. Okay, so we are going to find for the work done as your block moves from the equilibrium position up to the maximum stretching position. So if you're going to draw it, okay, so you have your spring. This is at x equals 0, and then let's say somewhere around here is your x max. So we're going to find the work done from this position here up to this point here. Okay, so it's the same process. You have your ws is equal to the integral of xi, xf, evaluated from xi to xf, of your fx dx. So this is the integral of 0 to x max of negative kx dx. So evaluating the integral, you have your work s is equal to negative k x squared over 2. You evaluate it from 0 to x max. Okay, so this is just equal to negative k x max squared over 2 minus 0. So you have this work done here. It's a negative work done. It's a negative work done because your displacement is going to the right, like say for example from the figure, okay, but the force which is applied by the spring is to the left. It's restoring it back again to the equilibrium position. The total work done as the block moves from negative x max to x max is 0. So that is, if you're going to find for the work done from at this point here, let's say this is at negative x max. This is your x equals 0, your equilibrium position, and then here is at your x max. So if you want to find for the work done from negative x max from this point here up to this point here, the total work done is equal to 0. So because from first you have 1/2 k x max squared for this point here, and here you have minus 1/2 k x max squared. So if you're going to add these two terms, okay, so you get total work done, which is equal to 0. If you're going to look at the figure here, we have this area here plus this negative, or plus this negative area here. So they just cancel out. So the work done from moving from here up to here is 0. Now assume that the block undergoes some arbitrary displacement from x is equal to xi to x equal to xf. Here, we're not talking anymore about the maximum compression and then the maximum stress position. Just some any arbitrary xi and xf. Like say, for example, just move it a little to the xi or you move it a little to the xf. The work done by the spring on the block is then equal to your 1/2 kxi squared minus 1/2 kxf squared. So this is your total work done by a spring. So your work done by a spring is equal to 1/2 kxi squared minus 1/2 kxf squared. Let's say, for example, let's draw some spring. Like say, for example, initially, let's do this one a different way. Like say, for example, initially your block is at x equals 5, and then you want to find for the work done when your spring is at x equals -2. So here, your xi is equal to 5, and then your xf is equal to -2. So you're just going, if you're given some value of k here, you're just going to substitute your values here. You have 5, and then here you have your -2 to find for the work done by a spring. If the motion ends where it begins, your work done is equal to 0. If, let's say, for example, you find for the work from here at x equals 5, and then at later time, you want to find for the work done going back here, okay? So whenever your motion ends where it begins, your work done is equal to 0. Because here, you have your work done for here, plus the work done to here. So it just subtracts your work that you do on your system. So if the motion ends where it begins, your work done is equal to 0. Now we also have this, what we call your spring with an applied force. This is when you're going to apply some force F. Like say, for example, applying a force in compressing your spring and then applying a force in stretching your spring. Suppose an external agent F applied stretches the spring. The applied force is equal and opposite to the spring force. Okay, as you can see, if you're going to apply some force here, F applied to the right, stretching the spring, your spring, again, with its restoring force Fs, applies a force of the same magnitude but in opposite direction. So here, you know that your restoring force is equal to -kx. So thus your F applied is equal to kx. Okay. So the work done F applied is equal to 1/2 kx squared max, as you can calculate. Okay. So let's end here.